Physics Part 116. Our third example, find the root mean square speed of the molecules in the nitrogen gas 27 degrees Celsius. The mass of nitrogen molecule is 4.6 into 10 power raised to minus 26 kg. Now it's your turn. Find the average kinetic energy of a molecule in an ideal gas at a temperature of 500 Ks. Number 2, find the root mean square speed of the molecules in the hydrogen gas at 500 degrees Celsius. The relative molecular mass of hydrogen is 2. I can deliver you a section summary. Assumptions of the kinetic theory of gases are: number 1, molecules behave as identical, hot, perfectly elastic spheres. Volume of molecules is negligible compared with the volume of containing vessel. There are no forces of attraction or repulsion between the atoms. There are many molecules all moving randomly. Kinetic theory PV equation, PV is equal to 1/3 nmc square. Average kinetic energy of a molecule is Ek is equal to 1/2 mc square is equal to 3/2 kT. Root mean square speed of the molecules, CRMS, is equal to √3 kT over m. There are few section questions. Estimate the root mean square speed of the helium atoms near the surface of the Sun, where the temperature is about 6,000 Kelvin. Mass of helium atom is 6.6 into 10 power raised to minus 27 kg. Question number 2. In the kinetic theory of the pressure of a gas, the impulse delivered by a molecule to the wall of the container is proportional to the velocity of the molecule. Why then does the kinetic theory equation of PV include the square of the velocity? Internal energy. Well, now we start another section of this chapter, and by the time we complete our internal energy section, we should be able to show an understanding of the concept of the internal energy. We should be able to relate our rise in temperature of a body to an increase in its internal energy. We should be able to show an understanding that internal energy is determined by the state of system, that it can be expressed as the sum of a random distribution of a kinetic and potential energies associated with the molecules of a system. We should be able to recall and use the first law of thermodynamics expressed in terms of the change in internal energy, the heating of the system and the work done on the system. We have seen that the molecules of an ideal gas possess kinetic energy, and that this kinetic energy is proportional to the thermodynamic temperature of the gas. The sum of the kinetic energies of all molecules due to their random motion is called internal energy of the ideal gas. Not all molecules have the same kinetic energy because they are moving with different speeds, but the sum of all the kinetic energies will be a constant if the gas is kept at a constant temperature. For a real gas, the situation is a little more complicated because the molecules of a real gas exert forces on each other. At any instant, there will be a certain potential energy associated with the position the molecules occupy in space.